Morning, everyone. Today I will be discussing our efforts to use simultaneous EEG and fMRI to enable dynamic network reconstruction in the human brain and hopefully convince you that this approach can facilitate and empower a level of neuronal understanding that extends beyond what could be inferred by either modality alone. We're ultimately interested in fusing information content across the two modalities and integrating that with behavior in order to offer a comprehensive characterization of when, where, and how information flows through the brain to guide behavior. We'll be typically starting with a specific hypothesis, a question that's rooted on firm theoretical ground, so that we can explicitly model behavior with an underlying mechanistic model in mind and use the model predictions to guide the fusion of the two modalities. For example, stratifying trials along a certain latent variable in the model to extract relevant neural representations, say from the EEG signal, and use them to inform the analysis of the functional data. Of course, this can also work in the opposite direction. One of the presumed advantages, in fact, of the fusion of EEG and fMRI is that they can offer additional explanatory power than, say, what can be achieved by behaviorally or model-derived predictors, which in turn could enable identification of latent brain states that would be unobservable with either modality in isolation. So in other words, this approach can be used to strike a good balance between a hypothesis and a data-driven analysis of brain data, and by extension could lead to new perspectives or mechanistic insights, if you like, that could be used to revise existing models and theories. So what's the underlying principle that would enable the fusion? Presumably, each of the two signals have some unique information content, but what we're assuming here, and we're ultimately interested in, is the shared variance across the two neuronal representations. In other words, we're aiming to exploit the overlap or the intersection, if you like, of the latent activity across the modalities that some people refer to as a common neural substrate. So how do we do that? So we would typically break the problem down into two broad categories, symmetric and asymmetric fusion. In asymmetric fusion, features of one modality are used as predictors of the activity of the other. This would be, for example, an EEG-informed fMRI design, or going in the opposite direction with an fMRI-informed EEG source reconstruction. During symmetric fusion, the data from the two modalities are treated equivalently. In other words, the fusion depends bilaterally on both data sets. We often tend to subdivide this further into data-driven approaches that exploit the shared covariance in EEG and fMRI jointly. For example, analyzing the two datasets independently, separately, and then using some form of representational similarity analysis, for instance, to expose the shared content. And finally, there's the model-driven approach that explicitly tries to model the neurovascular coupling across modalities, which is in fact a far more complex affair. Most of the evidence currently comes from invasive animal work, for example, using multi-electrode LFPs and metabolic and vascular measurements. Today, I'll be focusing on the most common of these approaches, namely the asymmetric fusion, whereby EEG is used specifically to drive the analysis of the fMRI data. So in a traditional fMRI experiment, we would have activations related to particular contrast or some task or behaviorally related parametric modulation. However, these maps, as you all know, are static, and making inferences about the relative timing and potential interactions across the brain nodes could be a challenge. Comparable analysis in the EEG would lead to a set of temporally specific events or components logged to a particular experimental event. And the goal here is to ultimately map the activations on top here onto these temporally specific EEG events to offer a more comprehensive understanding of the underlying network, so that we can begin making inferences about the relative timing of these activations and making more informed decisions on how to go about looking at interactions across these networks. So to do this, and that's sort of an important but subtle point, we need to exploit the endogenous trial-by-trial variability in the amplitude of these EEG components to build parametric EEG-informed fMRI predictors. Not so much the timing. Remember, these EEG components often are very transient. They come about with in rapid succession, often in tens or maybe a few hundreds of milliseconds apart. So given the sluggish nature of the fMRI, using the timing information alone won't be able to decouple these networks. So it's this endogenous trial-by-trial fluctuations in the amplitude of these components that would help us decouple the networks. So how do we go about extracting reliable information, single trial information from the EEG data? Different ways to do it. One popular approach that we've adopted in the past is to use multivariate discriminant analysis, whereby we estimate spatial filter weights, which we apply to the data to sort of collapse that multidimensional EEG space into a single aggregate representation, let's call it Y in this example, that discriminates between two conditions of interest. And ultimately use the distance of individual trials from that hyperplane that separates the two conditions as our endogenous trial-by-trial fluctuations in each of the conditions. And we repeat this across time, log to a particular experimental event to find all the time points that might lead to significant discrimination between the two conditions. And then we use those trial-by-trial Y amplitudes as predictors for the fMRI. We convolve them with an HRF and throw them into a standard fMRI GLM. We can quantify how well we can discriminate between conditions using ROC analysis, for instance, in the area under the curve or the AZ value, and also use a simple forward model here to get a first impression, a general idea of how these components might project onto the scope. So with that in mind, let me give you some concrete examples from some of our own work in reinforcement learning and decision making. So we're interested, for instance, to look at what happens or try to discriminate and identify the networks discriminated between positive and negative outcomes or outcome valence, for instance. So this would be an analysis log to the time of outcome, for instance. In a simple probabilistic learning task, reversal learning task, subjects would be chosen between two abstract symbols that have different reward probabilities, and through trial and error, monitoring the feedback, would learn to choose the one that's more likely to lead to a reward. So we've actually done this with standalone EEG in the past, and we've identified two components. Here is just the discriminator performance on the y-axis across feedback log time. And we found two separate components in the EEG that come about in rapid succession around 200 and 300 milliseconds respectively, discriminating positive from negative outcomes with very distinct spatial profiles. So at the time, we could only speculate that perhaps the first event is something that gives you a quick appraisal of the outcome along a good-bad axis, whereas the later one is perhaps some kind of more deliberate event that's related to value updating and learning. But we wanted to repeat this with simultaneous EEG-fMRI to actually try and understand and map out the networks associated with each of these components to see whether that interpretation was supported. We've done this recently, and we were able to, in fact, replicate those initial EEG findings. We've been able to map out these two temporally distinct events. Now we want to see how that maps onto the functional data. So a conventional fMRI analysis would be contrasting, in this particular case, positive and negative outcomes. We've done this analysis, and that's what you see here on top. And you see some regions that correlate more with positive outcomes, some activating more for negative ones. And as you can see, there's a lot of things going on here. These maps are very distributed, but also very static. Trying to interpret them can be quite a challenge. And I think that's one of the advantages of the EEG fMRI fusion, for instance, in particular in the context of these categorical variables, where the best we can do is just contrast them in this fashion. But here we are now, we have these two temporally distinct events in our EEG data, and we have this residual fluctuations, striatal fluctuations on top of that general categorical contrast that we can exploit and build fMRI predictors to decouple these networks. And when we do that, interesting things begin to unfold, and in a way that kind of paints a much clearer picture. For instance, the networks you see, or the activations that you see here on top, for the most part, they sort of trickle down, if you like, and they attach themselves to these temporally specific components in a way that kind of makes sense. We have this early system here, where a lot of these activations are responding specifically to negative outcomes and engaging areas of the brain that are involved in arousal and automatic response, premotor structures, as if this is an early alertness response to tell an organism that's of a potential threat, in case they need to flee a threat, before a more deliberate process of actually updating value representations, which is ultimately what we see here. This late system engages areas of the human reward and valuation system and responds along the full continuum of both positive and negative outcomes. The other thing I want to highlight is that, as I mentioned at the beginning, and it's particularly pronounced with this early system here, the statistical robustness of these activations is significantly improved compared to what you see in the conventional contrasts. Again, presumably because these endogenous fluctuations are meaningful in teasing these systems apart. In fact, we're seeing areas of the brain that were completely absent in the conventional analysis, and they're being absorbed by our EEG-informed fMRI analysis, in particular this thalamic cluster here, which is quite prominent in the early system. And of course, with this information at hand, we can then make more informed decisions, as I said at the beginning, of looking at connectivity patterns across these two networks. And in fact, we found a very reliable coupling between the thalamus, that unique cluster we identified with our approach, and the nucleus accumbens in the LACE system, whereby the thalamus ultimately downregulates the nucleus accumbens following negative outcomes, as if to say, now it's time to dial down, for instance, the value you assign to the option that just led to this negative outcome. And in fact, we took this a step further and we correlated the strength of that coupling across participants with behavior and things like learning rate from a simple reinforcement learning model and stay and switch patterns of our participants. And ultimately, the more aggressive the negative update or from the thalamus to the nucleus accumbens, the higher the learning rate on those trials, and the more likely the participant was to switch following that outcome. So ultimately, this gives us an opportunity to make more concrete inferences about the functional contributions of these networks. And that was an example of what might be happening at the time of outcome, but we're also interested in actually what happens at the time of the decision, when people make these choices. And there has been a lot of work, especially in perceptual decision-making, fitting sequential sampling models, and looking at evidence accumulation as a potential candidate mechanism of how people make choices. And more recently, people applied that to value and reward-based decisions. So we've done this here with simultaneous EEG-fMRI data. People are choosing between two different snag options, for instance, that they have previously rated individually. The value difference between the pairs determine how difficult individual choices were. And we've modeled behavior with a simple sequential sampling model in this case. And as you can see, we could fit behavior quite well. And we've done that through simulations so that we can, for each participant, also estimate an average profile of what their evidence accumulation plots should look like. And once we've done that, we could find EEG electrodes that exhibited a similar build-up. And we've done that. And we've identified subject-specific sensors that were capturing what the model was predicting. And once we've done that, we could then design an EEG-informed fMRI analysis, where we would then throw in a parametric EEG predictor that was modulated on individual trials by the actual trial-by-trial variability, endogenous variability in the decision dynamics. And we've included other potentially confound regressors like the value difference and reaction time to regress that out. And when we've done that, we found a region in the posterior portion of the middle frontal cortex, in fact, SMA extending down to mid-cingulate cortex, as being uniquely correlated with our EEG regressor. Now, this area has been previously linked with boundary adjustments, in particular during perceptual choices, but our data seem to suggest that perhaps it does a lot more than that, and that is, it in fact reflects the trial-by-trial, the full trial-by-trial dynamics of the process of evidence accumulation in the brain, and it speaks a little bit about the notion of embodied decisions when people need to externalize their choices with certain movements or motor actions. Perhaps these premotor structures do more than just indicate the decision. They might in fact accumulate evidence for that decision. And we've looked at the same thing using some kind of connectivity analysis where in fact this region of the posterior medial frontal cortex was ultimately correlated in a task-dependent manner with regions of the human valuation system in PMFC and the striatum, again making a lot of this makes a lot of sense, regions that might providing the value that's ultimately been integrated for the decision. And we've done the same, we've taken the same steps to look at the same decision-making period during our earlier probabilistic decision-making task I mentioned before. And as you can see, the blue outline is the cluster that we've observed in the value-based task, and the red here is from the probabilistic learning task, and that's quite a good overlap. Starting to kind of point towards a more general, potentially purpose decision maker. We've more recently, and this is a published work, we've tried to look at the same kind of thing doing social decision making, where people would be playing one-shot trust games, and the difficulty in the decision would ultimately be parametrically modulated experimentally by changing the trustworthiness of the phase that people were engaging with, whether they would invest in that particular or not, a particular subject or not. And we've also interspersed trials that were purely probabilistic, non-social in nature. For comparison, people were making choices purely based on probabilities. And as you can see, we could once again identify this build-up of activity in both social and non-social decisions with scalp topographies that are very similar, and then this same region of the posterior middle frontal cortex coming up, again suggesting a general purpose decision maker across these different domains, different tasks. So I would leave you with and wrap this up with some exciting new developments for bringing our EEG-fMRI into our 7 Tesla environment. And this process involved a great deal of hardware development, both on the fMRI side of things, with a new dedicated coil design to enable the measurements, as well on the EEG side of things, with a new cap design and new wiring profile. Since artifacts scale with the field strength, it meant we had to make an effort to minimize their impact at source, basically minimizing the surface area of our EEG leads, which in turn should reduce the inductive pickup on those leads. And this meant having to move the EEG amplifiers really close to our participants' heads and virtually eliminate completely the pigtail on the cap. So, and as you can see, this would have been impossible with the commercial coils that are completely closed in the back. And we had to build our own coil that was completely open, and we could really move these amplifiers next to our participants' head. And we compare the quality of the images with and without the EEG cap, and compared to the commercial system. They're brilliant, they look superb. no distortions from adding the EEG cap. And we've also recorded EEG data with this new setup, and we're able to successfully remove the artifacts. And you can see that the gradient artifacts are in fact 3 orders of magnitude than the recovered EEG signal. We're able to reliably remove the artifacts, and we're super happy with the quality of the EEG, comparable if not better with what we record in our 3D setup. And ultimately the goal here would be to use this setup to perform EEG-informed laminar imaging, for instance, to map specific EEG-evoked responses to different cortical depths, but also to use it to look at different subcortical pathways and structures, specifically as they relate to a lot of our work on decision-making and learning that would otherwise be unattainable with our 3D setup. Thank you very much for your attention. Thanks.